Today we'll begin our study of electricity, and first thing we'll look at is electric charge. The mass of a neutron and the mass of a proton are almost the same, while the mass of an electron is much less. Now, let's remember that the idea of where electrons are located. They're located on the outside of the atom, while the neutrons and protons are located on the inside of an atom. And as you can see, as I just said, the mass of the neutron and proton are almost exactly the same. But the mass of electron, even though it's really small, and so is the mass of a neutron and proton really small, the mass of an electron is even smaller. As a matter of fact, you would need like almost 2,000 of these guys to equal the mass of one neutron or proton. The electric nature of matter is inherent in the atomic structure as well. The charge of an electron is 1.60 times 10 to the negative 19th coulombs, and the electron is the same charge but negative. So the charge of an electron and a proton are exactly the same, but one's positive, one's negative. So what does that tell you? That means if you have just as many protons as electrons, you're electrically neutral. And when we measure charge, we measure it in what's called coulombs as a unit of charge. And as you can see, the charge of a neutron is 0 because there is no charge on a neutron. As I said, in nature, atoms are found normally neutral, which means they have just as many protons as they have neutrons. So by adding or removing electrons from matter, it will acquire a net electric charge, Q, with a magnitude equal to how many charges you have times the actual charge of one fundamental particle. So that could be summarized with this equation, where Q is a charge on the object, N is the number of charges times the fundamental charge. Alright, so let's try an example. How many electrons are there in 1 coulomb of negative charge? We know that net charge is equal to the number of charges times the elementary charge. We solve that for the number of charges. We would take the net charge as 1 coulomb divided by the elementary charge. Now, these actually both should be negative, but since they are both negative and we're only looking for magnitude, I left them out. And that comes out to be an answer of 6.25 times 10 to the 18th electrons make up 1 coulomb of charge. As a matter of fact, that would be the same number of positive charges that is needed to make up 1 coulomb of positive charge. So if objects are normally neutral, then how do we obtain a charge? In other words, is it possible to transfer charge from one object to another? Sure, but you have to remember that charge is only obtained on objects as it gains or loses electrons, because you can't gain or lose protons, because if you did, you would actually change the element you're talking about. So only electrons can move. So an example here is that you're rubbing a ebonite rod against fur, and you're stripping electrons from the fur onto the rod. So the fur becomes positive and the rod becomes negative. And as I said before, remember that only electrons can move, because you can't have protons move or it would change the element. You never actually create charge. All you're doing is adding energy to separate the positives from the negatives. In other words, you're trying to separate electrons from protons. This can be summarized in what's called the law of conservation of electric charge. During any process, the net charge of an isolated system must remain constant. In other words, it's conserved. You're never actually creating charges. You're just separating them. So here's some basic facts that you should understand, and I think most of you know. Unlike charges attract each other, so you have a positive and negative, they attract. Well, like charges repel each other. A negative and negative repel, and a positive and positive repel. Here's an interesting application of charges. This is electronic ink, like it's found inside of Kindles. You have a clear plate on top, a plate on the bottom that can be charged in very small little areas, and little beads inside. And inside each of these beads is a dark liquid and small little beads that are negatively charged. So if they're negatively charged and we charge the bottom plate positively, then you'll see dark liquid on top because the negative beads are attracted to the positive plate, and you get a dark image. If you charge the plate negatively, it chases away the negative beads and you see white, and so you get the white letters. So that's an interesting application of attractive and repulsive forces with electric charges. Not only can electric charges exist on an object, but it can also move through an object just as heat does. So heat moves from hotter to colder objects. Charge will do the same thing. It can easily move through some materials. Those are called electrical conductors. And some materials are very difficult for it to move through. And those are called electrical insulators. So how do we actually charge objects? One way is to charge it by friction. Here the ebony rod becomes negatively charged as it gains extra electrons. What you're doing is you're rubbing it against the animal fur. The animal fur loses electrons, therefore it becomes positively charged. The rod itself becomes negatively charged because it gained those electrons. Now you could also charge by contact. A charged object is touched to a neutral object, and the electrons are transferred. So this is a neutral object. It's insulated, so it can't lose its charge to the ground. And you bring a negative charged object to it, touch it, and they go into the metal sphere. When the rod is removed, the sphere becomes negatively charged. And so why do they spread out on the outside of the charge? The outside of the sphere. We'll talk more about that in class. And now we have charging by induction. This is really kind of cool. You have to really look at the images as I discuss it. This is a process of charging a conductor by bringing it near another charged object and then grounding it. So if you look at A, you have a negative charged rod. You bring it next to a neutral metal sphere that's insulated. So when you bring the negative next to it, it chases the negatives away, and this side becomes positive. Then the sphere is grounded on this side. The extra negatives don't want to be near each other, so they run into the ground. And then you remove both the grounding wire and the charged rod, and the overall sphere becomes positive. And you could also get a negative charged sphere by using a positive rod and allowing electrons to travel from the ground up to the wire to where the sphere is. There's other ways to do it as well, as we'll discuss in class. Can a charged rod induce a charge on an insulator? With an insulator, the electrons aren't really running away because they're fixed in place. But you could still get a charge on it. So how does that happen? If you have a negative rod, bring it next to an insulator, it chases the negative part of the atoms away, so the atoms themselves become more polarized, and so the positive side will be attracted to the negative rod. Even though this is electrically neutral, the very outside surface becomes positively charged. Okay, and this is very similar to when you rub a balloon against your hair. You get the balloon to be charged because it's stripping electrons from your hair onto the balloon, and it sticks to the wall, which is neutral, in this fashion.